Okay. When we look at symmetries in plane figures, we have either rotations, which in this case is going to be r squared. Why not r cubed? Brings you back to e. So these are the three rotations, r squared, and e. Then we had three, what did we call those? Reflections. And those were x, y, and z. Now, if you take your paper, rotation x is you grab 1 and you flip it. Rotation y is you grab 2 and you flip it. And z is, of course, 3 and you flip it. You okay with that? All right, so what we found out yesterday is if you go 1, 2, 3, and you go to 1, 2, 3, this is cycle 1, 2, 3, which is just E, right? But we could do one rotation R, 120 degrees. We could do 2, which is going to be R squared. We could do the reflection about the 1. We call this one X, 2, 3, 3, 2, but 1 goes to 1. And you could see the other ones following suit. What I thought was cool about these, this is Y, which is 1 goes to 3, 2 goes to 2, 3 goes to 1. And if you look at that as a cycle, what happens then is 1 goes to 3, 3 goes to 1, and 2 goes to 2. So it's simplified to that 1 goes to 3. Did we talk about the squares yesterday? Take your triangle, do the X flip about 1. Then do it a second time. You're back to E, aren't you? And that will be with all the reflections. You do a double flip, and you get back to E. So the dihedral set has E, R squared, X, Y, and Z. 1, 2, 3, 4, 5, 6 members. And we'll look at orders and all that good stuff. All right, so we got this is where I got to yesterday. If you take your triangle and you do nothing with it, you're to E, right? And so therefore, if we move all of these ER squared, EX, EY, EZ, it's just whatever that is. Where it gets interesting, oh, and you can do that on this side too. It's going to be the same thing. But what gets interesting is when we start combining these two, and that's why you have the two triangles. We're going to figure out this Cayley table, and you're going to fill that in. So what do you think the R squared is going to be? Or R, trying to be funny. R squared. Yep, that's the 2 rotations. So this will be R squared. And then what did we say if you do the R and then the R squared? R squared, what will that be? E, yep. Now is where it gets good. Okay? Now what we're going to do is we're going to do this one first because of the, when we do these rotations and permutations, we do the right first. So what you're going to do is you're going to do a flip here, and then you're going to do a rotation R, 120 counterclockwise. What do you end up with? I know, it's not super easy, is it? I thought it would be, but here. Okay, so what we did is we flipped them. We flipped them, right? So that this thing is about the X. So this is a 3. I don't know if this is going to let me do it, but I'm going to do it here. 3 and a 2. Because I flipped it, right? And then I'm going to turn it counterclockwise. That was kind of weird. I'll just group it, yeah. Then I'm going to turn it this way. Now, what is that the equivalent of? Notice that this is the same spot, but these two are switched, so therefore it's a what? A Z. Okay? Fill in the rest of that row. So after we did the activity with the triangles, we found that the Cayley table was closed. All of the A star B were members of the dihedral set, which were E, R, R squared, X, Y, and Z. They're all present in the table, each row and each column. So therefore, D3 is closed under star. Now the one we didn't want to have to do, and we don't, is the associative, because it's a bijection, meaning each row and column uses all the values, and we found that a composition of bijective functions is always associative. We saw that with the cycles. That was huge for us, because we don't like to 300 and what is that? 6 times 6 times 6, 316, something like that. Does this have identities? What's the identity? A star E or E star A is? E is A, so therefore E is my identity. So it can be seen from the table, A star E and E star A is equal to A. A is a subset of D3, therefore E is a subset of D3. And it is an identity. What inverses do you see? Tell me about them. Here's my E. Which ones are inverses of themselves? E and XYZ. Isn't that weird? That makes sense, though. The flips are inverses of themselves. And then R and R squared are inverses of each other. So therefore, you have E appears once in every column, is associative. Every element has its own unique inverse. Therefore, D3 is a group. It's called a dihedral group of degree 3. Written as a group, D3, comma star. We'll just do this example together. Label the vertices of the square 1, 2, 3, 4. State the order of the rotation symmetry of the square. Tell me about the order of the rotational symmetry. How many turns do we have to make until we get back? Yeah, it's an order 4 for each of those. How many lines of symmetry does the square have? Not infinite. Here's 1, 2, what else? 3, and 4. Can you see any other ones? So 1, 3 is a line of symmetry. 2, 4 is a line of symmetry. And then we would say the midpoints, I'm just going to draw these two. Okay. Write down each symmetry of the square as a permutation. So let's do this flip about 1, 3. What will that one look like? Yes, 2 goes to 4. And is that it? Because doesn't 1 go to 1 and 3 go to 3? What's another one? What's going to happen? Again, these are symmetry lines, not rotation lines. We've got our 4 rotations, but what's another cycle? 1, 3. What's another one? 1, 4, 2, 3. Brilliant. And what's the last one? 1, 2, and then you could go 3, 4. Yeah. So the order of this of each permutation, what's the order of this permutation? 2. This one? What's the order of this one? Yeah, Hanuk's right, 2. Because it's 2, 2, the least common multiple of 2, 2 is 2, and this will also be 2. And then it says, what's the order of the dihedral group? Meaning, how many rotations and symmetries are there? Let's see, rotations and reflections are there. That's the total of those for D4. Yeah, you're going to have E, which means sit there. You're going to have R, R squared, R cubed. How about R to the 4th? Nope, because that'll go back. And then you're going to have flips X, Y, Z, and A for Aiden. So that'll be a dihedral order of what? 8. Yep. What's the order of S4? It's interesting. And then you can look at those on your own.